Have you ever stopped and wondered what real, honest-to-goodness evolution would look like inside a computer? I'm not talking about a simulation of birds or fish. I mean the programs themselves, locked in this brutal, never-ending fight for pure survival. Well, what if I told you there's a digital world where that is happening right now? We're about to dive into a paper that brings that whole idea to life.
So take a look at this. This is not a glitch. This isn't a computer crash. What you're looking at is the memory of a virtual computer, and it is an active battlefield. Every single one of those colored pixels represents a line of code that's been written by a competing program. This is digital combat, where these little programs hunt each other down, they attack, and they literally overwrite each other's code to be the last one standing. It's wild.
And that really brings us to the core question of this whole research project. What happens when you apply honest-to-goodness Darwinian principles, not to biology, but to pure code? Can these programs actually evolve complexity, maybe even intelligence, through nothing but raw, head-to-head competition?
To really get how this digital evolution works, we first need to understand the arena itself, the place where these digital gladiators go to fight. So welcome to the battlefield. The game is called Core War. It was actually created way back in the 80s, and the rules are just so simple and elegant. You write a tiny program, they call it a warrior, and you load it into this shared memory space with an opponent. The goal? Simple. Be the last program still running. If your warrior tries to execute an instruction that makes no sense, it dies. The survivor takes the win.
And these warriors are written in a real, though, a simplified assembly language called red code. I mean, these are the raw instructions telling the virtual computer what to do. Move this piece of data here, jump to that memory location over there, maybe even spawn a whole new copy of yourself. It's basically the digital DNA of our little gladiators.
Okay, so here is the crucial piece of the puzzle. There is zero distinction between a program's instructions and its data. It's all just numbers sitting in memory. And that creates this incredibly chaotic environment where programs can do some clever stuff, like rewriting their own code to adapt on the fly, or, way more brutally, just overwriting their opponent's code with total junk, causing them to crash. It's a battle of pure information. So, you've got this insane, chaotic world. It begs the question, how on earth do you create a warrior that can actually survive in a place like that? Well, here's the problem. In a game like this, there is no single best strategy. It just doesn't exist. If you design the perfect defensive warrior, I guarantee someone is going to design the perfect attacker to break that defense. It creates this endless, escalating arms race. To survive, you can't just be good, you have to be constantly, relentlessly evolving.
You know, this whole problem has a really famous parallel, and it's captured perfectly by a character you probably know, the Red Queen from Lewis Carroll's Through the Looking Glass. She tells Alice that in her world, you have to run as fast as you possibly can, just to stay in the exact same spot.
And this isn't just some clever line from a story, it's a real-deal concept in evolutionary biology. It's called the Red Queen hypothesis. And it basically argues that for any species in a competitive ecosystem, evolution isn't really about getting ahead. It's this mandatory, never-ending race just to avoid going extinct. Because your predators, your prey, your parasites, they are all evolving right there alongside you. So with that in mind, how did the researchers actually create this Red Queen dynamic to evolve their own AI warriors? Let's break down their really clever method. They call it the Digital Red Queen, or just DRQ for short. Okay, so at its heart, DRQ is what's called a self-play algorithm. Basically, it learns by competing against itself. It uses a large language model to generate and tweak the red code for new warriors. And here's the key part. Each brand new warrior is trained to beat not just its direct parent, but all of its ancestors.
So the whole process is iterative. It all kicks off with one single basic warrior. Then, in round 1, the LLM evolves a new warrior whose only job is to beat that first one. But in round 2, the next warrior has a much tougher job. It has to be able to beat both of its ancestors. This just keeps going, creating this ever-growing historical gauntlet. Each new champion is basically forged in the fire of its entire family tree, forcing it to become more robust, more of a generalist, with every single round.
Now, this method is really smart because it solves two big problems.
First, the LLM acts as a kind of intelligent mutation operator. So instead of just making random changes to the code, it suggests logical, sometimes even creative modifications. And second, to avoid getting stuck in an evolutionary dead end, it uses an algorithm called map elites. The easiest way to think about this is that it forces evolution to explore a bunch of different options. It keeps a whole library of diverse warriors. Some are aggressive attackers, others are sneaky replicators, and this ensures that a wide range of strategies are always being tested and improved. It stops the system from just finding one little trick and sticking with it forever.
So the theory is solid, the procedure makes sense, but did it actually work? I mean, what happened in practice? Let's take a look at the results.
And the answer is, oh yeah, it worked. It worked spectacularly well. A warrior that was evolved against just one opponent becomes a specialist. It's great at that one job, but it only beats about 28% of a diverse group of human-made warriors. But the DRQ warrior, the one that was hardened against its entire lineage, it becomes a generalist. It is way more robust, and it defeats over 60% of those same human opponents. That arms race really does create true strength.
But this is where the research uncovered something truly profound. Now, to get it, we need two quick terms from biology. The genotype is the underlying code of an organism, its DNA, or in our case, the red code. The phenotype is the observable expression of that code, how the organism actually behaves, or in our case, the warrior's actual fighting style, what it does.
So when the researchers ran this DRQ process over and over again, they saw this incredible pattern start to emerge. After many, many rounds, the warriors' behaviors, their phenotypes, started to converge. They all began to fight in a very similar, very optimal way. But when they looked at the source code, the genotypes, it was still all over the map, completely different.
What they had stumbled upon was digital convergent evolution. This is the exact same phenomenon in nature that led to birds and bats independently evolving wings, or how eyes have evolved in dozens of separate lineages. You have different underlying code, totally different evolutionary paths, but they all converge on the same successful solution to the same problem. They discovered that in the world of Coral War, there seem to be these universal, effective strategies that evolution will just find, no matter how it starts.
Whew. Feeling your brain evolve a little bit after all that? Yeah, that's pretty much the Vibe Doc experience in a nutshell.
And speaking of that, our own analytics warrior has run the numbers, and it predicts you'll enjoy our other explainers. So you should probably prove it right and subscribe before some rogue paperclip maximizer AI, an AI that's so hyper-focused on its one goal it ends up destroying everything else, turns us all into office supplies.
Okay, but all jokes aside, this is about way more than just a vintage computer game. This research has some really serious, real-world implications. So what are the big takeaways here? Well, first, this proves that a simple, self-play arms race is an incredibly powerful way to create robust AI agents. I mean, imagine training a cybersecurity AI this way, right? Constantly evolving it against a whole family tree of its own past vulnerabilities to create a defense system that's a generalist, not a specialist. Second, that discovery of convergent evolution is a potential game changer. It suggests that for certain problems, there might be universal optimal strategies that will just emerge naturally from competition. We might actually be able to predict how adversarial AI, like computer viruses, will evolve. And maybe most importantly, Core War is the perfect testbed. It's a safe sandbox. We can study these digital arms races, which, by the way, are happening for real right now in cybersecurity and electronic warfare, but we can do it without any real-world risk. It's a way to explore these potentially dangerous AI dynamics without anyone getting hurt. And that leaves us with one final and pretty crucial thought. This work gives us this controlled environment, this little lab to understand and predict how adversarial AI evolves. But the real-world arms race, that's not a game. So the question is, are we ready for when this digital combat finally escapes the sandbox?